Hello, everyone. So in this video now, we're going to walk through Module 2 that focuses on using the SimCenter application quoFEM and OpenSys Pi to demonstrate how we can kind of use both of these tools for quantifying uncertainty in structural engineering problems, specifically those problems that count with experimental data of structural members and then deal with calibration of numerical models to that experimental data. Before we go to look at the specifics of the module itself, I wanted to say that the experimental results that we'll be using come from a database that it's openly available in the Peer Center that you can see here in the URL at the bottom. This is a database that has over 400 cyclic lateral load tests of reinforced concrete columns of 5 different type of experimental setups that you can see on the right of this slide. You're welcome to go look at that database. They made a tremendous effort to collect all of that information, experimental programs and campaigns done all over the world, and organize them and publish them in a uniform way, regardless of where the test was done. Now let's go and look at the module prompt, right? That describes the activities we'll be looking at, and we start kind of working our way through it. So let's see. Here is we open our module prompt, and let me reshare it so we make sure we're looking at what we should be looking. Yes, here you go. So here is the module prompt that you will be able to download from the SimCenter gallery website. Basically, and here is sort of the activity description. So in this problem, like it says here, the objective is to calibrate the structural model, specifically a model of a 2-element, basically a concentrated plasticity model that has a 0-length element on one end and an elastic beam column element that completes the entire length of the structural member, to then use that model and calibrate 3 parameters of that model based on experimental data that comes from that database I just mentioned, right? So let's look a little bit more about how that kind of experimental data is before we go into the specific questions we want to address. So to do that, let's look at the slides again. So here it is. So let me just share the slides here. There we go. So here is the experimental setup that the experimental program we chose. This is a series of tests that use the double cantilever column experimental setup, where basically the concept is that you have an element that looks like the image on the left, then has a block in the middle that's anchored to a wall or a strong base or slab, and then you have 2 symmetric columns on each side that at the end are connected to a couple of actuators on each side. One actuator responsible for applying axial force and one actuator responsible for applying lateral force, right? This one from left to right here. And the concept is that you will have that applied symmetrically in both sides, which theoretically then means that you can sort of simulate only half of the specimen, since the response should be symmetric. Here is a cross-section of the reinforcement on both sides, where kind of in this experimental program, they were kind of focusing on quantifying the impact of axial load, different levels of axial load, and different characteristics of both the longitudinal and transverse reinforcement. We will look at only 2 tests of that experimental program, one with axial load and one without axial load. In this video and sort of in the lecture, we will be focusing on the results without axial load and see how the calibration of the model looks like and what are the parameters we obtain. And then independently, you will have the opportunity to repeat these steps and recalibrate the model, but now for a different test that did include axial load during the process, and kind of see how the parameters of the model and the structural behavior of the member changes when you have axial load. So here is the example we're going to look here in class. Here is the force displacement response, where you kind of see that we kind of incur into nonlinear response. We have a first cycle that kind of goes up, and then that increase, that kind of response goes from 0.02 meters, so 2 centimeters, to 4, 6, and 8 centimeters. As I said, the idea is that you will take that model, that the experimental program, I will simulate it using this approach here. And the question that we'll have in mind is, what are the model parameters to simulate the behavior of this column using a plastic hinge model? So as you can see, we're already making some assumptions here, right? We have right off the bat decided that we're going to use a concentrated plastic hinge model, right? And that plastic hinge model uses a zero length element down here that will follow this type of backbone curve. So multilinear backbone curve that doesn't have cyclic degradation, right? So we are already making all of these decisions from the very beginning, right? When we decide that, basically what we're saying is that our model has only 6 parameters, or no linear response, and the whole structural model only has 6 parameters. It has some parameters that control the elastic stiffness, some parameters that control the initial elastic limit or plastic moment, then a capping moment, the corresponding rotation at that capping moment, and then a residual moment or capacity of that hinge, and the residual or corresponding residual rotation, right? From those 6 parameters, and we kind of go back and looked at the results of the experimental test that we are using to calibrate our model, it's evident that we have no information whatsoever from this test to calibrate both of the 2 latter line segments of our model. We didn't push during this experimental test the column far enough to have an idea of where the onset of degradation is, or how much is this degrading slope, and how much is the residual moment, and at what point in rotation you start kind of reaching that residual value. So we will only be concerned of calibrating 3 parameters. Some parameter that control the initial or elastic stiffness, 1 parameter that controls the elastic limit or plastic moment, and then 1 parameter that controls the second slope that we could also kind of determine based on what the capping moment is, and fixing or assuming a capping rotation, right? So this is the model we will kind of calibrate, and that's the first kind of question. So let's go back here and look at the model prompt and look at the entire model prompt or module prompt to understand what we're asking, and then we'll kind of walk through the solution to see how we can leverage quoFEM to solve this problem. So what I was saying is that the first is that the problem kind of and the step to follow to solve are shown here, and we have kind of broken up this module in the same sort of 4 steps, or the first 3 steps of the first 3 types of problems that one can tackle using quoFEM. The first type of problem is a parametric study, where we will kind of take our simulation model. In this case, would be in OpenCSPY, would be this model of the 2 elements that has a concentrated plastic hinge with our 3 parameters or unknowns, and then we'll take that model and we'll kind of interrogate the design space to see kind of what is the different ranges of responses that we can find for reasonable limits, lower bounds and upper bounds of each of the 3 parameters that we are interested in. Then we will do a deterministic calibration, which kind of focuses on the question of what is the set of parameters that would minimize the error from my model to the experimental measurements, right? This is a really common approach, and is how most of the model parameters estimations have been done in the past, but it has a conceptual assumption that the world is deterministic, right? It assumes that the measurements that you have done in the lab, of that, the research you're looking at did in the lab, is like the whole and complete representation of reality, and it doesn't have uncertainty around it, which is not true. And that kind of gives us our third and last part of this module, which kind of focuses on a Bayesian calibration, that it kind of flips the question, right? Instead of looking at what's the set of parameters that will give us our measured response, start asking what's the distribution, the likely distribution of those parameters that most likely produce the output that we measured, right? So that will kind of acknowledges that the world is probabilistic and that we have uncertainty both in the parameters but also in the measurements that we have. All of to solve this problem, we count with a starter code package that includes already the OpenSea's PY model of this column, and then some supporting files that, of course, include the experimental measurements for the column first, the one we're going to do in this video without actual load, and the one you're going to do on your own with actual load. And then, of course, we're going to leverage quoFEM to do this. And use also some post-processing notebooks that you can use in Google Colab or directly in Jupyter Notebooks in your local installation to kind of inspect the results a little bit farther from what the building capabilities of quoFEM. That may not be exactly the way you like to look at the results. All right, so now that we know what the module is about and what it's asked of us, let's start kind of looking a little bit more details about it. So let's get back to the slides. So let's see. We go back here to the slides. Oops. There we go. So the first thing that's important is to inspect our inputs, right? So what are the different files that we get on a starter code package, right? So as I mentioned, we have the OpenSea's model that already simulates the response of this column. We're going to open it in a second, but I just wanted to highlight here with this slide that this model, the construction of this model is nothing different to what you can see in module 1, right, in the OpenSea's PY module. Right, we first kind of follow all of those 10 different steps to create an OpenSea's model. We start cleaning the model, define the constants that kind of control this model, lengths, material properties, things like that. Then we define the material objects, create the node objects, assign supports or boundary conditions to those nodes, some of those nodes. Then create the elements, right, the zero length springs, the elastic beam column elements, whatever you need to simulate your structural member. Then define the lateral loads, or also axial or gravity loads in the case where that exists. And then finally run the cyclic analysis, which in this case is the type of analysis we care about, because we have a cyclic analysis that was done in the lab, and what we want is to replicate it now with this simulation model and try to calibrate the parameters so that we get the closest possible. Of course, it's important to recognize that when we're doing this calibration, we will need to run this model several times to kind of arrive to the best response. And just even from the first step on the parametric study, just to kind of inspect the design space, we need to run it several times. So it's really important that when we write these models, we consider that and we try to do it in the most efficient way. Let's, before going into each of the 3 steps, which I already mentioned, let's look a little bit more in detail how that OpenSea's PY model looks like. Let's make sure we will be sharing what we want to share. So let's go back down here to the starter code package. Inside the starter code package, you will find model files with pdelta for the case that you will do on your own, but you can also find on the background slide support files, the files without pdelta. And those are the ones we're going to use in this video. So you will find basically 4 files. And let me just show it to you really quickly. There you go. So you'll find 4 files: the column module, the column model, the column parameters, experimental displacement, and experimental force in CSV files. Let's go kind of through each of those to look at what they have. So let's start with the column model. Let's open it. Let's open it up here, maybe in PyCharm, but you can also open it in a regular text file reader, even Notepad or Notepad++, just the one I like to use, but there are different options just to kind of look at the code. And then you quickly see the similarities of you know, basically the structure, right, that follows the recommended structure for making a model in OpenSeas. So here we go. We got it here. Ended up opening it up in Notepad++. So let's make sure we are looking at the model. We should be. There we go. So here is the column module model. Excuse me. We start, and what's important to highlight here is that this would be the way in which we will set up a Python model or a Python script for use or proper use in quoFEM, right? This is not strictly limited to OpenSea's PY. It could also be the same kind of structure of this file or this script works if you have other type of model, if you're using other packages for structural analysis, or if you write your own sort of matrix solver for the system of equations. It will work the same way as long as it is on Python. So the idea is that you start sort of importing this couple, I mean, the system package, that's the only one that's required. Of course, in this case, we use OpenSea's PY, so we open OpenSea's PY as well. We wipe the model. We import the column parameters file. I will show you that in a second, but basically what that's doing is defining what are the variables, the random variables of the problem. So the variables that would be kind of changed through the analysis. And then we will define this function that's called run analysis, right? And that function, that is the function that will kind of do the analysis that we want to calibrate, right? So this is the one that builds the OpenSea's model inside, add all the loads and everything, and then applies a cyclic, the displacement control analysis, just like it was done in the test, right, in the lab, and would output the force history that the analysis will give, and that's the one we will compare with the force history that was recorded in those actuators during the test. So what I wanted to highlight here is the steps. You know, again, you start building the model, you put the constants, right, and geometrical constants, another type of constants. Notice how the Young modulus, the displacement at the capping point, the displacement at the residual point, and the ratio between the plastic moment and the residual moment, those are models or parameters of the model that we will assume constant, right? We don't have any basis to change those, especially these three, and then the elastic Young modulus, we are not going to change it because the only parameter we will modify to control the elastic stiffness of our member is the cracking factor, which you can see up here. So basically, what we are saying is the initial stiffness, the elastic stiffness of the structural member depends on, of course, the material, so Young modulus, geometric properties, length, and second moment of area, but also, since this is a reinforced concrete column, a cracking factor. And we are going to lump everything inside that cracking factor. And that's, again, another decision, right? We could also have another parameter and then kind of allow changes of our Young modulus, but that's something we decided not to do in this analysis. Then we define the materials, in this case, hysteretic material for the hinge, and then an elastic material with a really high stiffness to assign it for the translational kind of axial and shear deformation of the zero length element, which we don't want it to deform at all. Then we create our nodes at our boundary conditions, in this case, just fixing node 1. So we have node 1, 2, and 3, vertically kind of setting up our column. We assign secondary effects. For this case, we don't have axial load, so we will kind of work with a linear approximation. We will give us the same result as a P delta approximation since we don't have axial force. We create a spring element then, so this is then a zero length element that connects node 1 to node 2. We assign the rigid material for axial and shear deformations and assign our hysteretic material for rotations. Then we create the elastic beam column element number 2, from node 2 to node 3. We assign the same properties. remember the trick that we looked at in module 1. When you have this concentrated plasticity model, it's important to make sure that the elastic stiffness on the entire assembly follows what you will expect from typical structural mechanics. So for this case, for a cantilever 3I over L cubed, that's what you expect. But since you have a zero length element connected to an elastic beam column element, that you have additional sort of flexibility coming from the zero length element. So we will kind of artificially increase the stiffness of that beam column element, and you can kind of see it here in this theta y, how we computed that theta y using 3I over L, but multiplied by 10 times. So that means that we also need to increase a little bit more the stiffness of our elastic beam column element, such that the overall stiffness of our assembly follows the value that we expect for the lateral force 3I over L cubed. Then we define our lateral load. In this case is a force in degree of freedom 1 in node 3, so basically a lateral force at the top node. Really doesn't matter how much force you put, because the idea is that then we will apply or perform a displacement control analysis that will take the history of displacements that were applied during the test and will apply it step by step. Right, so, and we'll look in a second what is that this file is doing, right? The experimental test, or how it's set up basically. But you can imagine it's just a list of all the displacements that were kind of applied incrementally during the test. And what we will do is that we will kind of collect that displacement history and apply it, performing a series of displacement control analysis. So to do that, we define what's the node that we want to grab, what's the degree of freedom that we want to kind of impose the displacement, and how many steps we want to do in the kind of numerical solution for each increment in displacement. Then, since we are in OpenSys, we are able to define the different parameters for the solution of the system of equations. And then here in this for loop, we are kind of performing the displacement control analysis, right? Where we are kind of reading the displacement increment for each step that was done in the test coming from this file, and then doing the analysis step by step and saving the result, which in this case is the actuator force, or what's the lateral force that we're applying to kind of follow that imposed displacement, and we save it in this variable, the variable V cyclic, right? V kind of denoting shear force, and that's the only return of the model or of the results or the run analysis function. And then here we have a typical main function that if you're familiar with Python, you're familiar with this type of function arrangement. When we have a main function, that the only thing it does is that is running or run analysis and putting the result into this variable, the variable force. And that result of the variable force is getting written in a result.out file. And this is the file that quoFEM would be looking for after each run, right? This will be looking for a file called results.out, and that's the one that would be kind of taking to compute errors and see if the assumed parameters were proper or not for the calibration of the problem you want to solve. Notice that we none in this sort of function we have defined was the value of the cracking factor, what's the value of MP, and what's the value of MC. Those three, since those are random variables, those are defined outside of this function and inside this column parameters script. So let's look at it. Let's open the column parameters script. Here we go. Let's make sure we are sharing the file. There we go. And you can see it here, right? Very simple. Is just showing us that the value of the cracking factor for the initial value that we choose is 0.2, for MP is 330, and for MC is 240, right? So we just start with some initial values that we estimate, right? In this case, using reinforced concrete theory, we can estimate, assuming some Fy and F prime C and the section dimensions, we can estimate kind of ballpark what MP and MC should be, and we have an idea for the cracking factor value between 0 and 1, and we can assume some value there based on building codes, for example. And then with that, we'll have our starting point for the finite element model of this column. Now let's look at the experimental results. So for that, we go back to our kind of folder and open the experimental displacement CSV and the experimental force CSV. So let me open both of those and make sure we're looking at those. So let's look at first the experimental displacement. So here is the CSV file for the experimental displacement, right? As I mentioned before, it's just a column or a list of all of the incremental displacement or the displacement that was applied during the test. You can plot this to kind of have a better sense of what this is showing. You can do that here in Excel, and as we saw with the hysteretic the hysteresis loops that we looked in the slides, this is basically going in increments of 2 centimeters, right? So we go from 2 centimeters, 2 cycles, then 2 centimeters, then 4 centimeters, 2 cycles, then 6 centimeters, 2 cycles, and then 8 centimeters, 1.5 cycles. It missed one, the final branch. And that was the test, right? So this is the displacement that was imposed when they were performing the test. And now let's look at the result. What was recorded in the actuator, right? So to do that, let's go first close this file, don't save. And let's open up the experimental force. Here we go. So this is the experimental force CSV. Notice that we have arranged this file instead of a column in a row, right? And that's because that's how quoFEM expects outputs, right? quoFEM expects every output to be placed in a different column in the CSV file, which in this case means we have all of our results in a row. Why do we have so many? Because as we saw before, we have multiple increments in displacement. In total, to be precise, we have, let me see, 548 inputs of displacement with their corresponding output in force, right? So we have 548 columns in this file and rows in the other file, because we have a vertical kind of array that would depict the total information from the experimental results, the imposed displacement, and here the resulting actuator force. We can again kind of plot these results to look at them. And then here you can see, of course, how, for each of those cycles we looked at before, for the imposed displacement, we have a corresponding force, right? And now this kind of, you can see how they get to a certain value and then kind of gets saturated because we are in that post-elastic response when you get a plateau in the response. Just to confirm and make sure we got everything correct, we can open both of the files and plot the hysteresis loops that we were talking about earlier and that we saw on the slides. So here, for example, you can, let's see, go to the force, go here, and then we can insert another scatter plot. And then this scatter plot, we will select data, and we will select in the horizontal axis, we will select the displacement that comes from the other file. So here we go, 548 values, and the force comes from this file, 548 values. And there you go. There you have the hysteresis loops for the test data that we are interested in. So that's the way it should be formatted so that it can nicely communicate with quoFEM, right? So let's don't save anything here since we need those values raw. All right, so those are our inputs. So now let's start working with or solving the problem, or solving the module, right? So the first question in our module is perform a parametric study, right? So the parametric study, and let's just kind of go through the steps before start solving it. The parametric study in quoFEM investigates the influence of, in this particular case, of the three model parameters we discussed: the cracking factor that controls the elastic stiffness, the plastic moment that controls the elastic limit, and the capping moment that kind of controls that post-elastic stiffness of the nonlinear zero length element, the hinge. And then to do that, we follow these kind of 5 steps. We start setting up, we open quoFEM, we looked at how quoFEM looks like, and then we start kind of walking through each of the steps that start kind of defining the problem, which we'll define as a forward propagation with Latin hypercube sampling. Just because there's a convenient way to do a parametric study. Then we will choose Python as our finite element application, since we're using OpenCSPY, which is basically a Python script. We will assign, provide the column model and the column parameters model files that we looked at. We will assign kind of lower and higher bounds and upper bounds for each of the 3 parameters. Those are suggested here. Specify our quantity of interest of our output, which in this case is the force that has a length of 548 values, just like it was done in the experiment, and then we'll run the parametric study. So let's start with that. So to do that, you of course need to download quoFEM. The recommendation from the SimCenter team is to place quoFEM inside your local C hard drive or drive, create a folder called SimCenter, unzip the contents of the quoFEM file there, and then you will find an executable that says quoFEM.x. Another thing that I will further recommend is that you try to run this always as administrator. It normally kind of avoids some issues if you do it that way. All right, so once you do that, you will have quoFEM open, and you will have probably this view that you have here. So you'll be seeing quoFEM just like you're looking at here. So it will be interesting here at this point to look at the different steps to do a certain quantification problem in quoFEM. There's basically 5 steps, right? In the first step, you define your problem. So here you choose what's the uncertainty quantification engine that you're interested in. You choose the model category or the type of problem we're thinking about. It could be all the way from forward propagation to Bayesian calibration or generic optimization, and you can explore all the other ones. It's important to also have in mind that this look, it's really uniform across the SimCenter tools. In general, you can also, since all of these tools are in active development, you have the opportunity to influence how these tools develop. So you could go here to File or perhaps Help and submit bug and feature request, and that will send you to the SimCenter kind of site or forum where you can put your request and report issues that you can find in quoFEM while you're working on it. Or maybe if you have an idea of something that relates uncertainty quantification with instructional analysis and you don't find a way to do it properly in quoFEM, you can submit that request, and most likely one of the experts from the SimCenter will get to it and will be able to include it in the next versions of the program. All right, so let's start with that. So basically, in this example for a parametric study, we do a forward propagation with Latin hypercube sampling. Let's do 500 samples, and then you have a seed value that just for repeatability or replication of the results in case you want to replicate them exactly. Then you define the finite element model. You have several options here. You have OpenCS, and this is tailored for OpenCS Tickle implementation. Since we're using OpenCSPY, we will use the Python sort of finite element models, and there are other options here. So you go to Python, you define the input script. So you go wherever you saved the results or the starter code we just looked at, or look at the background model for the no P delta case. You upload it here, so you put it here. Post-process script, we don't need it because we are not doing kind of post-processing within a quoFEM. But then you do need the parameter script. So for the parameter script, we come back here and we define a parameter script. Column parameters, that's our parameter script. And what that's doing is basically populating our next tab, which is the random variables tab. So when you go here, you basically find the same kind of information that you saw, or almost the same that you saw on that parameter script, right? So you have all the names of the 3 variables, cracking factor, MP, and MC, and some default distribution, and the initial value that was assigned is assumed as the mean, and then it has some standard deviation. Normally the default is a 10% coefficient of variation. Since we are doing a parametric study, it's most useful to assume a uniform distribution, which basically means I don't know what this value is, but I'm confident of a lower and upper bound. So we do that for all of our cases. We define uniform distributions for all of them. And then we say, what are our lower and upper bounds, right? So for the cracking factor, we say that our lower bound is from 5% to 80%, from 0.05 to 0.8. For MP, we're going to say goes from 100 kilonewton meter to 500, and the same for the MC. You can always check the PDF to see if it aligns with your assumptions, to make sure it's taking a uniform distribution or whatever distribution you assume. The next tab defines the quantities of interest, or the engineering demand parameters, EDPs. In this case, we're interested in the force that has a length of 548 values. And with that, we have everything ready for parametric study, right? Notice that we haven't provided the program any information from the experimental test, right? And that's because we are not interested in simulating that, right? We're not yet quantifying any error with the experimental test. The only thing we're doing is running the analysis for a range of lower and upper bounds of our parameters. So it's also important, and I should point this out, that the displacement time history, or the experimental protocol that was used, the displacement protocol, is in the same folder where your models were, right? Where the column model and the parameters file, the scripts were, because especially that displacement is an input, right, for the column model. So it should be in the same folder, so that when quoFEM goes look for those models, it knows the inputs are in the same folder and drags them to the running folders. All right, so with this we can hit run, and you see at the bottom here the program output. It's kind of doing the analysis. Is basically running 500 times the displacement control analysis, the cyclic displacement control analysis, using different sets of the 3 parameters of our model, right? This kind of sampling this based on our uniform distribution, using Lightning hypercube sampling so that it can better describe that distribution we assume, saving the results, and then will give us some basic distribution or understanding of the distribution of those outputs. The outputs would be kind of assumed as 548 outputs, right? One force value for each of the analysis steps that are done in this experimental test. So that's what we will expect to see in a second here when the analysis finishes. Notice that when quoFEM is doing its work, and this is also very common in all SimCenter tools, when things are running, it tends to kind of the GUI, the graphical user interface, stops sort of responding. Right, so you will see here how if you try to move things, it will get non-responding, but that's a good sign because it's doing the things in the background. All right, the analysis finished, and you can see here the results. So now the results tab would be filled, and as I was saying, you will have the result here as 548 kind of values that you can see down here. Your 548 values. Each one of those has 500 values inside. And what they're showing you here in this kind of first screen with the results is the mean, standard deviation, skewness, and kurtosis of those 500 underlying values. But of course, it's a little bit more interesting to look at the underlying data, right? So for that, we go to data values, and here you see the distribution, like the list of what's exactly the cracking factor MP and MC that was used in each of the 500 runs that we asked the program to do. And of course, here on the columns, you have the 548 results corresponding to each of these kind of sets of values. So we can save this result, save this table, and we can just save it somewhere. For example, let's do it out here. So class parametric study. Save. All right. So with that, we have solved the first part of the problem. It would be interesting to also inspect the results and then see kind of how that looks like. But we will do that with our quoFEM, or not with our quoFEM, but with our Google Colab notebook that will help us kind of inspect the results a little bit better. But before we do that, let's run all three using quoFEM, and then we go into inspecting the results in detail. All right. So now what's the next question in our module? So let's look at the module again here. Let's share the screen again. Here we go. So the next question is to perform a deterministic calibration, right? So here again, we are looking for the value of crack factor, MP, and MC that minimizes the error from the model compared to the test. To do that, we will, instead of doing a forward propagation, we will do a deterministic calibration. We will use the NL2sol, so the nonlinear two solution method inside quoFEM. You can look at the documentation for more details on what's exactly the algorithm that's used inside here. And for this, we recommend to use a maximum of 1,000 iterations and a convergence tolerance of 0.0001. Of course, now we need to provide what's the experimental results, right? Because we are actively comparing against those experimental results. So for that, we will kind of upload that, and we'll repeat the steps kind of in a very similar fashion as we just did before. So let's do it and see what happens. So let's open quoFEM again. One recommendation here is that every time you do a different analysis, you close the software and close quoFEM and open it again as administrator optionally. And see how to do the analysis. All right, so let's look at this. Let's share the screen again to make sure we are looking at quoFEM. There we go. So here we're looking at quoFEM. Now the problem, instead of, is we're still using Dakota as our UQ engine, but instead of doing a forward propagation, we will do a deterministic calibration, and we will use the nonlinear two solution, the defaults 1,000 and 0.0001 as our convergence inputs or parameters, and we choose the calibration file. So we go here to quoFEM, background slides, and then we say we want the experimental force that was recorded during the test in that kind of raw format as our calibration data file. Then we repeat the steps we did before. We choose our model as a Python model. We define our parameter script. That will populate our random variables. Notice that here they're not asking us for a distribution, right? A probabilistic distribution, but they're asking us, how do we want to treat these random variables in our calibration, as a continuous design or as a constant value? Of course, in this case, we want it as a continuous design, and we know our bounds, right? We want from 0.05 to 0.8. The initial point could be the same one we have predefined in our column parameter script or file. We want this to go from 100 to 500, and the MC again from 100 to 500. We define our output as force, the quantity of interest, 548 size, and we hit run. And what this is doing is that now is evaluating, but we're using a clever optimization algorithm, and that's when the UQ engine capabilities become evident, right? To find where what's the set of parameters that minimizes the error between the experimental tests and or numerical simulations. And this is the result we get. Right, we get that the best parameter for the cracking factor is 0.26, for MP is 289, and for MC is 317. We can look also into what was the kind of the path that the model took from the very beginning, right, when the initial values that you set, to arrive to this best set of parameters. And you can see that if you look at data values, you can see how that kind of evolved, right, for the cracking factor, for the MP, and from the MC, right? You can see how that changed, and you can see how many runs were done. In this case, were done about 10 runs. We can save this table, and we can save it out here. Maybe we can save it as class deterministic calibration. Save. All right. Perhaps let's go look at how that table looks like. So we exit quoFEM, then we go to the folder where you save that file and open it up. There we go. So here, let me show you. Here we go. Here is how the calibration looks like. So you get all of the runs, and then the value of each of the cracking factor, MP and MC, and organize all of the 548 outputs for each of those kind of sets of results. Internally, what quoFEM is doing is that is comparing this output, right? This 548 results is comparing it to the experimental results, right? That we input at the very beginning. And the way he's doing it is by minimizing the sum of the square errors for each of these parameters. That's the default error function that quoFEM is doing for every problem that you define, right? So you can also kind of tweak the problem, and inside that run analysis subroutine or function, you can also quantify different outputs. And instead of having one output here, all the 548, you could have something different that uses an alternative error function. But if you don't do that, then the kind of default error function is the sum of the square errors. Notice how the runs are not organized here, are not in order, right? They are kind of in a random order. So it would be good if you want to see this evolving, organize it, so we can kind of filter this or sort it from the smallest to the largest. There we go. So now we see we started here, right, from the initial values from 0.02, 330, and 240. And then that started changing following this clever optimization algorithm until we got to these parameters that are the best parameters. All right, let's save this file and close it. All right, now let's go back to our module prompt and see what is that we need to do at the very end. Again, we're going to inspect the results a little bit more in depth after we finish running quoFEM. So the last part of this module is doing the Bayesian calibration problem, in which we, instead of looking for the value of the parameters, we are looking for the distribution of each of the parameters, cracking factor, MP, and MC, that best represent the model uncertainty corresponding to the measured response. So to do that, we at the very beginning, we are going to use the UCSD UQ engine, so not Dakota anymore. And we will use the transitional Markov chain Monte Carlo method that's implemented and available for our use thanks to quoFEM development or developers. And this will do a Bayesian calibration that could take a lot of time depending on how many number of samples we want. Because what this is doing is that it's taking our simulation and is running it multiple times per simulation or per sample, because what they want to know is what the analysis is doing in rough terms is solving is using Bayes' rule, right? Starting from a prior distribution that it's assumed automatically by the model, a likelihood function that's also what the prior function we determine, and then the likelihood function could be automatically defined by the model in the transitional Markov chain Monte Carlo, usually a Gaussian distribution or Gaussian likelihood function, and that will change and will give us then a posterior distribution. And what we get is the number of samples that we ask of that posterior distribution, or samples from that posterior distribution, I should say. Then we define the Python finite element model application. We assign our prior distribution. Like I say, the recommendation would be to assign a uniform distribution with the lower and upper bounds we've been using here, the same quantity of interest, and then we run the analysis and save it with a model, the name we define. For your work, we have a name recommended here, but you can change it. And then when we're doing post-processing using we will call it notebooks, make sure that you do it. And we'll do it in a second when we start inspecting the results a little bit more. We will run into the details of how to upload these files and make sure the names are interpretable. All right, so how do we do that in quoFEM? So the same thing, we go here, open quoFEM as administrator. Yes, we open it. We have it here. And then we make sure we are sharing quoFEM GUI. And then, as I said, we start UCSD UQ engine, transitional Markov chain. we're going to do 100 sample size of outputs just because we want to limit the amount of time this will require. You could do this perhaps utilizing the capabilities of running in design safe, so on high performance computing resources instead of your own local machine, and run a lot more simulations, like 500 simulations or something like that, to have a much better description of that posterior distribution of the parameters given the input. Then here we define our calibration file, of course, or a calibration file would be the results from the experimental test, so experiment force, we define it there. Then finite element analysis, we have a Python script. That Python script is this column model, and we have a parameter script, this column parameters script. We get our random variables. For this example, we recommend defining a prior distribution as a uniform distribution. We don't know. You know, you can go kind of insert prior knowledge here. Like, for example, if you know that, say, the MP has a distribution or could have a distribution related to the Fy of the reinforcement, you know, the yielding stress of the reinforcement, you could then have an argument to say, instead of a uniform distribution, I'll have a log normal distribution and define the lambda and the zeta of that distribution. But we're going to start, you know, ignoring that type of knowledge and just assuming lower and upper bounds, the same as we have done before. And the uniform distribution here from 100 to 500, the same from the MC 100 to 500. The result, quantity of interest, force, 548 values, and then we're ready to run. So we send it to run. This will take a while, as I mentioned, because it's evaluating the function multiple times. So while this is happening on the background, let me show you how quoFEM organizes the analysis files under the hood, right? Not on the GUI, but what's happening behind it. So to do that, you will most likely have a folder called quoFEM in your documents folder. So you go to documents, you'll find a folder called quoFEM, automatically created by the program when you open it up the first time. And let me show you what you will see in that folder. So when you open that folder, you see this, right? You will typically have a folder that says local working directory, or even another one that says remote working directory if you have sent any job to the design safe computer cluster. If you have only done local jobs, you will only have this top folder. You can go inside and you'll find a temporary sim center folder that gets deleted every time you run a new analysis. So that's why it's kind of important to close the software and open it again so that it kind of refreshes everything and doesn't carry over things from the previous analysis you did. You open it here, and then you typically find this. You have a template directory, and that template directory includes the inputs that you place, right? So in this case, you will have the column model parameters, the column model script, the column model parameter script, the displacement, which is an input for the column model. And then outside here, we'll have the target, right? The experimental force. This will be the target. And then each of these working directories is kind of a clone of that temporary, you know, that template directory, but then with the specific assumptions of the input parameters. So you can go here and then, for example, say, what are the parameters we assume, right? So this file here, you can open it up with a text file reader, you know, maybe Notepad or something. And then you will see there what is the specific value of the cracking factor, the MP and the MC that quoFEM is using for this particular simulation, right? And this is how it's doing all of those. We ask for 100 and it's doing it 100 times, but each of those, you know, inside each one is changing up because of the Bayes rule and the way the algorithm, the transient Markov chain algorithm for Bayesian calibration works. All right, so this is still running in the back, so let's just let it run a little bit more. So while this is running, let's now look at our post-processing scripts that are available for your use. So here you'll find at the starter code for what you need to use, the same kind of post-processing files that I will show you and we would use here for or background slides or for in-class example. So when you go into here, you'll find basically two notebooks, right? A column model notebook and a post-process quoFEM notebook. So let's start looking at the quoFEM notebook. This is basically the same, the column model notebook. This is the same model in OpenC's PY, but now done in notebook scripting. So you can kind of play a little bit more with it. So let's open it up in Google Colab. So you can open it up in Google Colab. There we go. So let's make sure we are showing it. Okay, so here it is in Google Colab. So the first step, again, as we did in module 1, is start installing OpenCs. Then we import the packages we want, and then we define some inputs for our problem, right? We define the inputs of our problem, the length of the column, material properties, section sizes, rebar, axial load. All of these, specifically the information of the rebar and the material properties, is not really necessary with the exception of the young modulus of the concrete, but all that is kind of already defined. It's necessary for only this one is necessary for the creation of the model. You will see it in a second. In this case, we don't have axial load, so we define it as 0. And then here we have a few options here. So one of the things we want to do, what this file does really, is that it compares the analysis from the OpenC's model with the experimental results. So we need to upload the experimental results, right? And as you know, with Google Colab, we are in a virtual machine, a machine that lives in some of the servers from Google. So we need to upload on that server, on that virtual environment, the results of our experiment. So to do that, we'll use the files upload function. We choose the file. So we go up here, background slides, and upload our displacement from the results, and then our force from the experimental test. And those are uploaded. You can kind of check here, if you see this symbol here on the left, you can go there and make sure that your files are uploaded. Now we want to read those files into a list inside Google Colab. Here you can see kind of some hand calculation as I've done to kind of show, to have an idea of how this concrete column behaves, right? We computed the actual crushing force, what's the stiffness that you would expect, right? So 3I over L cubed. And then estimate kind of what would be sort of the balance moment, the balance force, and the balance displacement, to have just a rough idea of where would you expect this column, at what type of value of MP you will expect, more or less, right? Of MP and of course, force, lateral force. Here you can define the model parameters, and this is a good place for maybe comparing what happens with the deterministic calibration. So if you remember from the previous part of the second part of the solution, we found that the cracking factor, the optimal value was 0.26, for MP was 289, and from NC was 317, right? So since that was our finding, let's put it here and compare it, but now graphically, like kind of overlaying the experimental results from the analysis results. So we can run that. We have some fixed parameters like we discussed before. We don't have enough information to change. And then start the OpenC's model, which is basically copy pasting from the run analysis function script that we looked at before. So we do that. Then we can view the model using the ops function. We do the cyclic analysis. We can see the displacement protocol, cyclic analysis, and then here we overlay both results. So here you can see how well the deterministic calibration does, right? You can see on the top the force in time sort of overlaid in red the model, in gray the experimental test, and here the hysteresis loops. Again, in gray the model, in gray the experiment, in red the model. Notice how our model doesn't capture, for example, this smooth transition down here, right? And that's because of the decision we made from the onset of assuming that the hinge is a series of line segments, right? Our model is just rough enough to capture these changes in forces, but doesn't have the resolution to capture these kind of smooth transitions, right? We could have a more complex model that instead of having this, linear segments, we'll have a more smooth plastic hinge, but that will include additional parameters, right? So it's always a trade-off when you need to choose how many parameters you are willing to calibrate with the uncertainty that comes with. And what type of model you like to use, and how or how close you want to replicate the results of your test. So this part will never be able to, this type of model will never be able to capture it well. All right, so this is one way to look at the results, right? So kind of solve based on inputs and look at it dynamically with the notebook. Let's see how our quoFEM analysis did. Seems it's still running. So now let's look at the other output post-processing script. So our other post-processing script is also right next to the one we just looked at, is the post-process quoFEM. So we can open that in Google Colab, open in Google Colab or Google Drive. Then that will open it up here. All right, let's look at it. There we go. So here it is. So here is the second file. So you go here, open post-processing results, and then the first thing that it will ask for is for the inputs, right? So the inputs is basically the results of all the analysis we did plus the experimental results. So what's the experimental for CSV we got, from the test, then what's the result of the parametric study, the deterministic calibration, and the Bayesian calibration. We don't, they just finished quoFEM. So let's put a hold on that output and look at quoFEM for a second, and then come back here. So let's look at quoFEM. Here we go. So quoFEM just finished, and how do we know? Because the results tab is now full, right? So you can see here for each of those parameters, the inputs, and then all of the outputs, the 548 force values have a result. You can look here in diagnostics, some summary of the results, but the most interesting in data values, in data values, you can see kind of the final 100 samples of the posterior distribution of each of the input parameters, cracking factor, MP, and MC. We can again save these results as a table. So you can save it as a table. We have saved it here in class. So then we call it class page saved. And it's done. And that gives us all of the inputs to use our post-processing script. So we go back here to Google Colab, post-processing script, and then we will upload all of the results, right? So we do that using the files upload again. So we say, okay, choose file. So we do the experiment force, which is the output. We're comparing things again. This is necessary for really looking at what's the error in our parametric study. Because that wasn't calculated in quoFEM. quoFEM gave us the force, the 548 results for each of the simulations we wanted to do. Now we need to calculate the error outside. Then we can choose the files for each of the other analyses, right? For each of the parametric study, that would be the class PS file. That would take a little bit because it's 500 simulations, 548 results per simulation. Then we choose the results for deterministic calibration just to see the calibration path. And we choose our Bayesian calibration results, class-based. Notice how the name of the file is a little different than the one that is sort of recommended here. So you need to make sure that now when we start loading those files into variables in the notebook, we use the proper name. Again, you can go back here on the left and make sure that you have kind of uploaded correctly those files. So then we know that our parametric study results is not called like that. We call it class PS. So we make sure we call that class PS. Deterministic calibration is called class DC, and Bayesian calibration is called class Bayes. So we upload those. So all of those are now in a list. Then we get the result from the deterministic calibration. the parametric study and Bayesian calibration into proper sort of variables. We compute the error. So again, here you can see we are doing the sum of the square error between the force that was predicted of each of these simulations and the force that was recorded in the test. And then we can output the results. You have, you're welcome to look at how these figures are created using Matplotlib and Python scripting. And this is the result, right? Here is the MP compared to the cracking factor and the MC compared to MP. This is sort of the space of all possible results you can get and from the parametric study. And the bar chart or the colors of each of these dots denote the error, comparing it to the value that was measured in the experiments. So you can see in red the lower errors and in bluish the higher errors. The black kind of line here depicts the path from the deterministic calibration, right? The point where we, when the analysis started, right, with an MC of 300, 330 perhaps, and 290 perhaps here, and then how we kind of travel to find the outputs that we obtain as the optimal values. Then we can also plot the Bayesian calibration results. And those, again, instead of an exact value, is a distribution. So you can see what's the distribution of the cracking factor, the distribution of the MP, and the distribution of the MC. Notice that we can also compare the mean of each of those distributions with the deterministic calibration results. In the deterministic calibration is the one shown in red. You can see how they are similar for this problem to the mean of the Bayesian calibration, but that's not always the case. It all heavily depends on the type of problem you're trying to solve. And then perhaps more interesting here, you can plot now what's the relationship of the distribution of MP and MC and MP and cracking factor and even MC and cracking factor, right? Because now what we got is that with the Bayesian calibration, we can capture correlations between the inputs, right? You can see, for example, here that MP and MC are heavily correlated, right? When MP is high, then MC must be low, such that, for increasing the likelihood of you observing the outputs that you got from the experimental test. So basically what that's trying to do is to give you what's the relationship between those parameters. So in the case that you are able to measure one, you have an idea of what is the value of the other one. So this is how you can sort of use the post-processing script and look at the results. Let's go back to the slides to kind of close this session up, looking a little bit more inside the results and kind of summarizing what we have done here. So going back to the slides, again, the result of the parametric study is just kind of an evaluation of the design space. The error is the sum of the square error if we haven't defined anything different. And this is a really good way to kind of understand how far are we and what's kind of the range of the error, right? We're seeing that for this problem, the range of the error is like a value, less than 1, right? And in the good regions is about, really lower than 0.1. That's important because when you're then defining, say, the tolerance in the error, it would be good to know what's sort of the range of low error value, like what's a low error value means. The parametric study also kind of helps you show what, where are the locations that have high errors, so very unlikely combinations of parameters. But then you can inspect it a little bit more if you compare it, right? If you compare your model to the experiments in each kind of the extremes of that design space. So for example, in the top left here, if you have a low value of cracking factor but a high value of MP, what that's saying is that you have a really low initial stiffness, but then you yield really far away. So that would be in red, the response that you got there. In contrast, if you are on all the way to the lower right, if you have a high cracking factor, so you have really high elastic stiffness, but a low MP value, then you have really high stiffness, but you yield really quickly, right? And then you get those hysteresis loops that are really far from what was measured in the test, and thus the high error. Then you can also look at the conventional calibration. This is the example that started from a different initial points. And then you can kind of see how they both compare, right? And this is what we just looked at using the post-processing notebook, and look how we can kind of relatively well describe what was measured in the test. Now, for the Bayesian calibration, we are now not only focused on the value, but the distribution, right? What's the distribution of the parameters given the observation of the experiments that we obtain? And for that, we use Bayes' rule that uses the evidence in green, which was the test, but also uses a prior distribution from the parameters, and also a likelihood function that relates the evidence with the parameters. And that's usually an assumption from the algorithm, from the Bayesian calibration algorithm we're using. And this is kind of the example of the results. That again, that's multiple model evaluations, and that's why it takes significantly longer than the other two calibration methods. So that's sort of the summary of what do we do in this module, where we can do all of these 4 kind of questions in the module. We exercise the first 3, and the fourth, which is the only one we didn't exactly kind of perform in this analysis, is very similar to the parametric study, but instead of assuming uniform distributions, we will assume, or we will use a distribution we already know for the parameters. So that's why it's called forward propagation, right? Because you already know the uncertainty in the inputs, and you propagate it through the model until you get to the outputs, and you can describe the uncertainty on the outputs. And that's a forward propagation. So with that, you will have the chance to kind of repeat parts 1 to 3 of this module, but now with a different experimental program, or a different experiment from the same experimental program that has actual load. And that will kind of give you the opportunity to see how the actual load changes the response, how adding P delta effects also affects the response, and then those values of cracking factor, MP, and MC change when you have actual load. And then you have the opportunity to kind of analyze the nonlinear response of this column that's otherwise identical to the one we did, is just just having actual load. With this, I'll thank you very much, and I hope you enjoy and learned a lot from this module. Thank you.